Hello. We're going to talk about a new law. It's called Ampere's law. So we're going to compare that to Gauss' law that we studied before in the electrostatics. So what's the difference here before we get into the law? So this is talking about the electric field. And this is referring to the magnetic field. Okay, so this is field. And in terms of geometry, this is talking about a closed surface, a closed surface. And this is talking about a closed loop. It doesn't have to be a loop, it can be any shape, okay? So what's a better word? So this is the geometry. Geometry, okay? And inside the surface, this one here has static charges. So the charge doesn't move, does not move. But inside the closed loop here, well, it's not a loop, it's just a close, close, like a close, anything like that. Close, okay? It's not exactly a loop, but yes, it's, well, it's not a circle, but it's a loop, okay? All right, so, and this inside there, this is current. So current, it's moving, but the charge is not moving, okay? So this is what's inside, right? And they both require the operation. They both require summation, okay? They both require summation. And they're both talking about what's inside the loop and what's inside the surface. So inside the loop here is the current, right? So this, and what's inside the surface here, it's the charge. All right, so with that, we're gonna get started with Ampere's law. So let's give you, so these two laws are two of the four fundamental equations for electromagnetism. Okay, so electromagnetism, and these are the two equations, the Gauss's and the Ampere. All right, so let's talk about the Ampere's law now. So Ampere's law says the following: if I have current, so it doesn't have to be one, it can be multiple, right? So it can be multiple, it can be 2, 3, 4, but let's just draw, like two of them right now. And then you are looking at closed path, okay? The closed path is surrounding this guy here, this two, okay? So this is like a closed path, okay? So that's a must be closed, okay? Closed path. And this is surrounding, right? So this is surrounding the I1, I2. Right? I1 and I2. And so what you would do is the following. So you would do like, you cut this into small pieces, okay? Small enough that inside each piece, the magnetic field, it's a constant, okay? And you only want to look at the magnetic field that's parallel to it, all right? So you may have magnetic field going this way, but you don't care about the one that's perpendicular. So you look at the magnetic field that going this way, so B parallel. And 1, okay? And then this one here will be the delta L1, all right? So then you would take that term, B, call that B parallel, but 1, and then times delta L1, all right? So then you would, you treat them like a scalar here. and then you plus the next term. So next term is going to be, say, here, right? So that's delta L2, and then B2 will be going, the B2 parallel will be going that way, B parallel 2, okay? So then you plus B parallel comma 2, delta L2, right? So you keep going until you finish this summation here, right? So you finish up to here, right? So you go and then you finalize at, at the end right there. So where am I? So right there, right? So then this is your last one, okay? So 1, 2, 3, 4, blah, 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 up to here, let's say 100, okay? So then you have the B parallel 100. Let's say 100 is good enough, okay? Just for example. And so that's that. And then so you have the B, right? So you add, right? And then the final one is parallel, and then 100, delta L 100, okay? So you add them all together, and then that is equal to this mu zero that we talked about, the permeability, right? Permeability of free space, okay? Of free space, which is equal to, I think, 4 pi times 10 to the negative 7. And I forgot the unit, okay? You can go figure it out, from before. So right here, right? So this is mu zero times the I total, that's enclosed, okay? Enclosed, right? So this I, in this case, the I enclosed, right, is equal to I1 plus I2, all right? Okay? So that is your Ampere's law. That is so-called the Ampere's law, M's law, P-E-R-E law, right? For magnetics. So you can find the relationship between B, so summation B, and that's called that one B parallel, right? B parallel I, and then delta L I, right? I from 1 to N, right? And that's equal to the mu zero times I enclosed, okay? Remember in Gauss law, what we have is we have summation, and we have E perpendicular, right? And then times the delta A, this is the area, right? And still I 1 to N, which is equal to Q enclosed, right? Q enclosed divided by the permittivity, right, of free space, okay? So one is divided by and one is multiply, and one is the charge and one is the current, and one is the area, one is the length, and one is electric field and one is magnetic field, and they both need to do the summation operation. All right, so that's all we have. Hopefully you will get to understand the similarity between Ampere's law